Okay, so today we okay, so today we will in this class we will deal with mainly the searching algorithm. So any one of you is familiar with any of the searching algorithm? Have you heard of it? How is it? So searching algorithms are basically like you have given an array, you have to search an element in the array. Oh, thank you, thank you, thank you. Yes, linear and binary. Yes. So we are going to discuss those searching algorithm today. Okay. So okay. So let's start. So the first problem we'll discuss is this one. That just a second, I'll be back. Okay, so sorry. So, in this searching algorithms. So the first so the first one we do is binary search, but in general, like for this problem, the input is given an array, and A is an array or list, whatever, and a key. Let's say K. K is the key. So output or the question, or you can say it's a question, is does A belongs to A or not? And if yes, then the position of K. Uh, yes, right. Okay. So this linear, linear search is thing. So the first problem we'll deal with is the binary search. It's a very easy and basic problem. So it works on see, the binary search cannot be applied to any like not any array. Okay, so there is a restriction in the input, and you will understand why. Uh, Input should be A is a sorted array. and the key. Okay, and the question is same. Okay, so how does binary search work? It's like, suppose you have an array A. Okay, so it has, let's say, n element array. Okay, so it has let's say some element. Okay, 0 it can be 1, 5, and some more elements than 100. So it's a sorted array. First A is sorted. So you have to search, let's say k equal to some 10, maybe 10. Okay. So let's say you need to search 10. So 10 would be somewhere in the in the after 7 and below 100. Okay, 100 or 90. So the algorithm works is like it's a kind of divide and conquer. It's not kind of, it's a divide and conquer algorithm. So are you familiar with the term divide and conquer? No. Okay. So see, okay. So when you design an algorithm, like merge sort, yes, merge sort is a divide and conquer algorithm. Uh, so it's actually a technique. Okay, divide and conquer means that you have a main problem. So you have, what is divide and conquer? Is that you have a main problem. This is your problem, let's say. So what you do is you divide it into parts. Okay, smaller parts. You divide this problem into smaller sub problems. Are called sub problems basically. So you divide this problem into smaller sub problems, then you keep on breaking it until they are like very easy to solve. Okay, so you break it, let's say, up to this. These are the easy problems to solve. Okay, so now you solve them, and then you keep on solving the, like, parent means you solve these two, and then using that solution you solve this one, you solve this one, you solve this one, and then you solve the original problem. So that's the divide and conquer technique. Okay, so this is what more or less a rough idea of divide and conquer, but there are more uh, actually there is a lot of things inside. So I think it will be covered in your class. So just for the name divide and conquer, this means that you have a problem and you are dividing it into smaller sub problems, and you're solving that smaller sub problems and use that solution to solve the bigger problem, original problem that you have started with. Okay, so now you have to, let's say, uh, so what we do is that we find, so steps of algorithm. Okay, so first step is find the middle element of it. So let's say it's binary search. The top today, I'm starting with binary search. So let meet see the be the middle element. Okay. Now what you do is you will compare your key with the middle. So if the key is equal to your array mid, then you already have the answer that yes, it belongs to the array. Otherwise, key is less than array mid. Now what you can do? If your key is less than array mid, so let's say the middle element in here is around, let's say 20. Okay, so your key 10 is less than this middle element. This is your array middle element. So now what to do, that you don't need to search, since it's a sorted array, there is no need to search in this portion. So you can discard this portion after mid, and you can search in the this rest of the portions, right? So if the key is less than array mid, then you search or repeat the same steps actually. Search in the search here, and if the opposite thing happens, that key is greater than array mid, then you will search array n-1. Okay, so this is the step. Okay, so let me take a small example of how this works. So this is your input. So in here you can see that you will search in this portion for 10, and if 10 is present, then it will be inside this region, otherwise it will not be there. Okay, in the array. So 10, 20. So there are 6 elements in this array. And what is the middle element? So it's even number of elements are here. So you can select either 9 or 10 as a middle element. Let's say 10. You can easily choose 9. Yeah, I mean, both are okay. Okay, I am n-1 actually I've started index with 0. So if you have an n element array and your index start with is with 0, then your last element, the index of the last element should be n-1, right? So that's why it's from mid to n-1. If you start your index on function, which function? कोई फंक्शन यूज नहीं होता इधर. नहीं, यहाँ पे कोई फंक्शन यूज नहीं हुआ है. मैं ये एरे का इंडेक्स कहाँ से कहाँ तक है वो डिफाइन कर रहा था. ओके, सो ये यहाँ पे नहीं, मैं यहाँ पे फंक्शन मैं डायरेक्ट मैं फंक्शन की तरह यहाँ पे नहीं लिखा हूँ.
और पहली बात तो ये कि फंक्शन ये तुम मतलब ऐसे फंक्शन मैं मुझे ये समझ नहीं आ रहा है कौन सी फंक्शन की बात करो, क्योंकि यहाँ पे कोई फंक्शन यूज नहीं हुआ है। ये a mid n-1, दिस इज रिप्रेजेंटिंग array. Hello, it's okay now? हाँ, तो ओके, सो वो फंक्शन नहीं है। हाँ, हाँ, इट्स ओके, इट्स ओके ना, आई थिंक इट्स फाइन नो। सो यहाँ पे देखो, एरे तुम किस तरीके से डिफाइन करोगे उसके ऊपर n या n-1 डिपेंड करता है। अगर तुम स्टार्ट कर रहे हो n से, मतलब 1 से स्टार्ट कर रहे हो, if your array starting with 1, so you have a1 a2, then you will go continue up to an. Otherwise it's 0 to n-1. It's not like always it will count n-1. Okay, so don't think like that it will always count n-1. It's depending on what is your initial index. Okay, fine. Now okay, so now you have your middle, and your key, let's say, is, so say 9. Okay, so your key is 9. You have the middle element as 10, so you compare this. So it obviously 9 is less than 10, so you will search in this array. Now your array is modified into 2 7 9, because 10 is not in the 10 is not equal to 9, so you don't have to consider 10 itself. You can discard the middle element. Okay, you just consider the element right next to the middle. Okay, so now this is where you need to search, or you need to go for the second step or second iteration, and your key is again 9. Okay, now what, this is a 3 element, the middle element is 7, so here array meet is 7, so your key is greater than actually array dash meet, right? So now your array will become this one. So you look at this subproblem and your key is 9 and there is only one element 9, so you have that 9 is present. Okay, so see, you started with this array, then you discard all this part, you just take this part, which is almost half of it, and then you again discard like half of this, almost half of this, and you come up with the solution, whether it's present or not. You can take any key element, you can take any element like okay, there is also like you can judge it quickly if the number is already, since it is a sorted array, if the number is always smaller than the initial element and bigger than the uh, last element, then it will never be inside the array, right? So that's a quick judgment you can make based on the observation. That's how you can modify even binary search, because you don't need to like repeatedly doing these steps, because here what I am doing is that I am actually It's a recursive process. First, I apply the process on the whole array, then I divide it into smaller array, almost half size, and then I apply that process in there. Okay, so in this way, you can actually modify the this binary search algorithm. So let me write the pseudocode for it, and then we'll go for running time. Okay. So this is a function binary search. Our array is A and the key is K. So if array meet is equal to K, then yes. Else if array meet is greater than K, then you apply binary search. So your middle element is bigger than K. So you have to check from 0 to mid minus 1 array, right? Up to K for this key K. And otherwise, then we call the same function, but now we'll look into mid plus 1 to n minus 1. Okay. Okay, fine. So this is the pseudocode for this problem. Okay. So any questions till now or any doubt? Okay, so I guess it's fine. Then what would be the running time of this problem? So running time. So we compute the running time for this problem. So what we observe that at each step, what we are doing, we are almost dividing the array by half of it, right? We are considering only one half of the array after each recursion. So yes, log n. The recursion corresponding to this problem will be something like this. Okay, why n by 2? Because we are almost like, you can use the lower floor or height, whatever, but still it should be like, you can easily write it like n by 2 and order one. Why? Because at each iteration you are just checking whether K is greater than that element or smaller. So that can be done in order one time. And at each iteration you are dividing the whole array by its half. So this is the recursion corresponding to that one. And how to solve this? Have you have done something like this previously, I think. So you can keep on repeatedly doing this. Order on plus order on, which is nothing but. And if we continue in this way, you will continue up to some k steps. So till this n by 2 to the power k equal to 1. And from here you can get k equal to log n. Okay. So your running time order log n. Okay. Okay, so it's fine for everyone. So now can you tell me what is the problem with the unsorted array? That why we cannot apply binary search in unsorted array? What is the problem with unsorted array? Why we cannot apply this binary search in unsorted array? Okay, if it is not sorted, then you cannot manage to use the idea that you can discard the half of the array by just checking the middle element. Okay, if it is not sorted. So now what if the array is unsorted? Can you devise an algorithm? So if an array is unsorted, then how to search? So now the problem is that you have an array, it is unsorted, or you don't know whether it is sorted or unsorted, and a key. Okay, so key. So question is whether A is in A or not. So how can you deal with this problem? Yes, whether to go left and right. No, it actually take time. You cannot discard actually. It will not based on the time. Yes, yes. The middle element logic is correct. Okay. Yes, linear search. So what happens in linear search? In linear search, it's just actually a brute force method basically, right? So what do you do in linear search? Does anyone have any idea about linear search? And how this algorithm works? Comparing every element from the start. Yes. So what do? You have your key. You compare your key from the start of the element. Okay, element of the array. So suppose you have an array. let's say let's take this one that we have 2, 7, 9, 10, 13, 7, 9, 10, 13, 40. Okay, so let's start with this array, and our key is 15. So then what do you have to do? We check the first element whether it's 15 or not. So it's not 15, we discard it. Then we go to the next element, whether it's 15 or not, we discard it, and we proceed in this way, and till the next there is the last element of array, and it's not 15, so 15 is not present in the array. And if you change the key to 13, let's say, so you'll check from the first, not 13, not 13, and you reach here, okay, it matched, then it's then 13 is present in the array, and the position is this one, is I think 5th position. So this is the linear search algorithm. Okay, so what is the best case for linear search? So in binary search there is no best or worst case, you have to check. Or in binary search even there is actually a best case that I discussed, that if the element is bigger than the uh, largest element, the last element of the array, and smaller than the first element of the array. In both cases, binary search will run in constant time. In here, first will be the key. Yes, if the first element is key. Yes. So if it is the first element is in the key, then you know that it's. And then you will directly get the solution. So it can solve for the best case running time. Order 1, and the best case corresponding to first element of A is the key. And what is the worst case? Last element target, or the element is not present in the key. Last element of A is the key, or the element is not present in the key. The key is not. Okay, so not only the last element, I mean, you can observe that if the element is not there, you have to search the whole array to find the whether it's there or not. So still you have to cover the whole array. And why it's the worst case? Because you have to check every element at once at least. So the time consumed by this is order n, right? Length of the array. The worst case running time is order n. Right? So on an average, this linear search will take order n time. Okay. And its corresponding pseudocode is very easy, so I'm not writing this one. I'm skipping this one. Okay. Fine. So now, okay. So next, in the last class, I have discussed about some techniques, right, to solve the recurrence relations. I think you remember, and I discussed one of them. It is called recursion tree in your class in the last tutorial. If you remember, we did that merge sort with 1:3 ratio, and in that, to solve that one, we used
this recursion tree method. So today we will yeah,
It's audible now. Hello. Okay. So okay. So today we in the last class we have discussed while solving this that recurrence corresponding to the merge sort problem with 1:3 ratio. We have discussed a technique to solve this reconciliation called uh, recursion tree, if you remember. It's kind of tree-like structure. I showed that you divide the problem into these parts, and then the longest chain that will continue, you have to calculate that one, and that will give you the total running time. Okay, so today we will discuss some of these techniques to solve the reconciliations. Okay, so today's topic is now next is reconciliations. Okay, so we discussed how to solve reconciliations. So there are actually 4 methods. First method is method of substitution. Second is change of variables. There is third variables. Okay. And then there is iterative method. Oh, 5 methods. I mean, iterative method and the recursion tree is actually the iterative method and recursion tree. They are quite similar to each other. So you may consider them as same methods. Because if you have an iterative method, you can construct a tree from there. Iterative methods for recursion tree that we have already discussed, and there is fifth master method. Okay, so among all these methods, I have discussed this one last time in the class very roughly. Maybe I'll discuss a little bit more about it today. This one will be covered by sir, so I'm not covering this one. So we will do mainly these 3 methods in today's class. Okay. So now the first method, the method of substitution. So substitution actually works in this way that you have a reconciliation of, let's say, this form. Suppose you have a reconciliation of this form. C Okay, so your reconciliation is something like this, where this A, B, C, these are constants. Okay, so you have an idea about this order notation, I think. So, right, order notation. What is representing big O, small o? So you know these things, I hope. And now, so you know that these constants actually have no impact on the running time. Basically, it's the function of n that matters. And now, suppose your recurrence is of this form. So then you can use this substitution method. So the method works as follows. So steps to apply substitution method. So basically you guess the solution from this. If this is given, then you try to guess the solution. So make a guess. And how to guess? How to guess? It's actually very difficult to um, say how to guess, because there is no particular way to guess a solution for some recurrence relation directly looking at it. But in some cases, like you may see, this technique has a drawback actually, because you have to guess the solution, which is like which may not be working in every situation, and it might take quite a lot of time to find the right case. So this is not a good technique to apply, but it's kind of effective when there is like simple solutions. It's depending on the form of the functions. It's depending on this constant c, depending on these constants a, b, and everything, and the function also fn that's given. So it's everything is depending on, or your guess is depending on these factors. So make a guess of the solution and inductively find the constants. This induction to find the constants. And show that the solution works. Okay. So let's try an example. Okay. So this is the given recurrence. This is example 1. Okay. So what could be the guess for the solution? See, one thing is that I'm sure if you break this term, if you think about n greater equal to 1 cases, then each time you have to break this will occur some 2 to the power something like that. Okay, if you look at this term, it will like if you consider some large cases, large values of n. So whenever you break this tn minus 1, whatever it's going on, like tn minus 1, tn minus 2, if you go like this way, your uh, recurrence will follow some 2 to the power k type thing, right? You can guess it from there. So from there, you can guess the value of, you can guess that, okay, it would be something like the running time would be something like 2 to the power n. Okay, now look at the constant. 2 to the power n will not work. Why?
because the base case, it is the base case, right? So n equal to 0, it's 0. So in 2 to the power n, it would be 1. It's not 0. So 2 to the power n minus 1. We can take that one. So our guess will be 2 to the power n minus 1. Okay. So this is also one thing to observe, that based on A and B, because if B is something else, I would have chosen something else. And mostly based on A, I have chosen this function. Here A equal to 2. If you want to like make a resemblance between these two things that I have written, here C is 0. Here let me write C equal to 0, A equal to 2, and B equal to actually 1 in this case. Okay. If you want to transform this one into that form. So my guess is this one, that the solution is 2 to the power n minus 1. Now, let's say we have to prove it that this solution is the correct solution. So we'll prove using induction. So for induction, we have to check the base case. So in the base case, what happens is when n equal to 0, t0 is 2 to the power 0 minus 1, which is 0, right? So 2 to the power 0 is 1, ct. So base case holds. So it holds. Now induction step. So let's say the statement is true for k minus 1. So that means tk minus 1 equal to 2 to the power k minus 1 minus 1. Okay. So now we have to prove tk. Tk is what? 2tk minus 1 2tk minus 1 plus 1. So which is, we have already seen that this is nothing but 2k minus 1 minus 1 plus 1. So this means this is 2 to the power k minus 1. Okay. So this is true for k. So implies that the solution is this implies that tn equal to the power n minus 1. So that means the running time will be some order 2 to the power n. Okay. Okay. Fine. Any question? Okay. Fine. So let's go to the next. So let's see another example of this one. Okay. So
So next example is this one. Is 1 if n equal to 1, 2t this is floor function when n greater equal to 2. Okay. So what can you guess in this case? What should be the guess for this? Is it still 2 to the power n? Or it's something else? Is it 2 to the power n, or can we use the same solution in here? So it doesn't work, right? To the power n doesn't work. Why it doesn't work? Okay, you verify whether why it doesn't work. It will fail the induction steps. Um, check it. So in this case, let's say, let us assume the solution of this form. Let me guess. C is a constant, okay? I mean, n log n is a guess. C is a constant. Okay, so now, like if it is true for some, so what do you have to show? That if it is true for some k, and also you have to verify the base case, but you can see that the base case is not verified in here, right? Because if you put n equal to 1, the log 1 is 0, so it doesn't hold. Okay, so can we write, so let's say our base, let me take this solution and think about this part, that whether this C n log n thing works or not. Okay, and like why I am thinking about this C n log n is because if you break this, if you think about this term, and you can write it as t n by 2 plus n. Okay, now if you break it and you think about this as a C n log n, so what would be the solution? 2 t c, sorry, let's say for n by 2 it holds, then it's C n by 2 log n by 2. Okay, if it is true for anything less than n, so okay, just let me write it properly, otherwise get confused. Suppose the statement, which statement I'm talking about, this one, is true for any value less than n. Okay, true for some x less than n, let's say. So I'm talking about anything less than n. So this n by 2 is a less than n value, so it will hold. So we can break it into this part. This plus n, which is nothing but Cn log n by 2 plus n. So you can write it as Cn log n minus C log 2 plus n. So this is nothing but Cn log n, right? For all c greater or equal to 1. So now see, your it's showing that, okay, if it is holding for anything, any value less than n, then it's hold for n also. So but the problem is with the base case, because the base case is not holding in this case. So what we can do is we can shift the base case, because if you remember the running time, and if you remember that what we are doing by solving these recurrence relations, we are computing the time complexity, okay, of the recursive algorithm, or whatever, recursive algorithm basically, of that recursive algorithm, that the one which we want to compute. So in the to solve that recursive, so our target is to find the running time, right? So what we try to do is, if you remember the definition of the running time, I mean, definition of the order notation. So order of n means what? That your function will follow n after a certain value. Okay, it may be a certain, there exists some n0, if you remember the definition. There exists some n0, so there would be a value after that. The function would follow this n, the linear function, the multiple of n. So this means that you can think, you can this n log n is still the running time. It can be the running time, because if I shift my base case from one to some other, I discard just one case. Okay, it's not holding in there, it's not a problem. For running time, for me, it's okay if it's working from 2, 3 or something. Okay, because because in the rest of the part, for the rest of the part, it's following the same procedure. So this would be, so our running time in this case is Cn log n. Okay, so this is basically the merge sort that you have done. If you remember, this is the running time of merge sort. Okay, so you can compute running time in this way too. And you remember, in the previous case, someone said that 2 to the power n is the solution, and 2 to the power n case was not holding for n equal to 0. Yes, so ultimately your running time, if you compute the running time, this is nothing but order 2 to the power n, and in your case it's also order 2 to the power n. So both cases will give you the same results. Okay, but like to show that these cases, to prove the induction, we just use that one. But to find the running, so our target is to find the running time using these recurrence relations. That's why we if we are seeing that all the rest of the function are all the rest of the values, the function is following some other some function of n, like in this case for every value is following n log n except for one. So we can discard that value and we can still consider that n log n part as our solution. Okay, so this is kind of a tricky thing in here. Okay, so this method is not so good because it's depending on the guess, and as I've said earlier, it's very difficult to guess which one could be the right one. Okay, so next method is change of variables. Okay, any question? Any question regarding this? No. Okay, fine. So next method is change of variables. So suppose you have a reconciliation. So it's something like you have a value of n, you just substitute the value with some other uh, other integer, let's say, instead of n. You use that to make it a like easier structure, and then you solve it. Okay, so let me let me show it by an example. So root 10 plus log n, and also remember that log is base 2 in here. Every log is of base 2. Okay, so now this we consider let m equal to log n. So this means 2 to the power m is equal to n. So now this reconciliation would be transformed into something like 2 to the power m by 2 plus log 2 to the power m, which is log n is m. So you can think of it as m. Okay, so this 2 to the power m by 2 term is I mean like t of 2 to the power m, t of 2 to the power m by 2. So can I think of it as something like this? Can I write it? Can I write this into this way? Where s is another function. I'm transforming this t to the power m equal to 2 into t to the power m by 2. Yes. We can write how we can write this one. Can you find the similarity between these two I mean, why these two functions are similar? Because I am considering this as this sx is t of 2 to the power x. Okay. So if we consider this function sx as t of 2 to the power x, then your sm is t of 2 to the power m, and your sm by 2 is t of 2 to the power m by 2. Clear? Okay, so from here it follows that we are getting this one. Okay, we can write it. Then now this is known. We have just seen, we have just solved one of this. We can write it as order n log n, right? That is some constant multiple c into n into n log n. Okay, so oh sorry, it's m. Sorry. M. So this is order m log m, which we know is something like m log m. C, where c is a constant. So this implies that we know the solution. Now we can so we can just transform it back to our case. So e to the power 2m is equal to order m log m. Now what we have seen that 2 to the power m is n. So this means that Tn is equal to order m means log n. So it's log n log of n. Okay. So this is how we solve it. So it's another interesting technique, but it's also like this technique also is a little bit difficult because you have to change the variable in such a way that uh, you can form you can transform this reconciliation into a simpler form. Okay, for example, like you are dealing with root n in here, the factor log n helped. If the log n is not there, then this could transform into something else. This could have transformed into something else which could be like hard to solve. Okay, since this considering m equal to log n helped us to transform it into a known form, we did it easily, but like there could be difficulties. Okay, so this is one of this is another method, and iterative method I think you have already seen when you solved this running time for March sort. I think if you look at that note, your running time of March sort, that one is actually what you are doing. What if you remember correctly, the recurrence is something like Tn equal to 2Tn by 2 plus order n, right? It's something like that. And you just doing it like 2 square T n by 2 square plus order n 2 cube T n by 2 cube plus order n. I mean order n you can write it as Cn also. Then we don't use equality. Cn Cn plus Cn is Cn plus Cn plus Cn, and in the end it's like 2 to the power k T n by 2 to the power k plus Cn this k times. So this 2 to the power k n by 2 to the power k, this should be 1 when you stop. So k is your log n. is your login. So this would be equal to order n log n. So this method that you repeatedly solve this one is the iterative method. This falls under iterative method. And for recursion tree, you can take that example that we have discussed in our previous class for the merge sort. That one I think would be sufficient. So is it fine for everybody, or is there any questions? Is there any question? Okay, fine. So you can try to solve some recurrence relations on your own. You can find a lot of examples and you can apply one of these techniques, but the best technique is master method and the recursion tree. Mostly it's recursion tree for the known algorithms, or for the mostly used algorithms. It's recursion tree can give you the running time easily, but these methods are also sometimes effective, change of variable and substitution method, but the guessing part is a little bit difficult. Okay, so if there is no question, then I'm shifting to the coding part. Okay. Okay, so for coding, for today's problem, today we will do first we will do this binary search, and then if there is time, then we can do the linear search or some other problems. Okay. So let's start. So I think binary search is quite easy since we have done a lot of already done the necessary things. If you that you need to write a program on this binary search, because we have done problems on array, we have already used functions. So using those same things, can you write a code for this binary search problem? I mean, try to write a code for binary search problem. I will.
It's visible, I guess.
Everyone see my screen? Can all of you see my screen? Okay, fine. Okay, so write the function. So I'm writing the recursive method that we have studied just now. So first I will write a function that will represent the binary search process. Okay. So this function, what should be inside the function? An array and its indices, because since we are breaking this into middle and uh, the rest of the part, so we have to give the input of like from where to start and where to end in that array, right? So we will give those indices and the key. So this binary search function will contain the array. I think someone was talking about some function in the beginning. I think you wanted to mention this, I guess. So it's actually depending on the code, like how you want. So integer one is index is the smallest index at the start of the array. So let's say start, and another is at the end, and another is the key. Okay, so what do you need to do? You need to find first. You need to find the middle element, right? So if your start is this, then I record the end. Then your middle, this should be equal to you have to calculate the middle. So what should be the middle? It should be from the lowest, or if you are using highest, then high minus, or if you are using low, then low to half of these elements, right? So you will do with the starting index. So start to the difference between the start index, the end index, high minus the start index divided by 2. Okay, this should be the coordinate of the middle. This should be the position of the middle element. Okay, is it clear? Like for 0, it's for 0 to n minus 1, it should be n minus 1 by 2.
So now that you have calculated, you find the middle, then what do you need to do? So once you have the middle, next you check if your key this is greater than key or less than key. So if it is greater than key, then what do? You just call the same process, binary search on A with our start be the same and n should be now middle, right? Because you have to search in that portion, and obviously mid -1 and to the key. Okay. So if this is the case, get else. So in the else case, you just call it for the rest of the part. +1 and okay. So call it and it will be done. So after this process, if there is if this element is present, it will be covered. If you reach at the end of this process, that means this is not present in the array. So we end it. That in that case, it will return some, let's say, something -1. So now let's write the main function. So we have this key, then teacher. This is solution. So now you can specify that if solution will give you the value, solution will return. So this function will return either the index at which the point is, or it will return the return -1 that is not present. So if solution is -1, and got to mention, I think what if it's equal? That case I did not consider. It should be returning the value missed. Should be else. Okay, it's correct. Yeah. Actually, I missed that one. I added it. What do we have in our example? It's 6 millimeter. Okay, so you can see it's giving the output. Okay, Is there any difficulty in this code, or I think it's very easy. This one was easy actually. So can you guys try to write selection sort based on this?
Selection sort is actually simpler than this one. You can directly write selection sort. So I just want to see one code from selection sort from you guys in C. I know you guys can write this code in Python, maybe in other languages, whatever language you are comfortable in. But can you write this one, the selection sort in C?
Paste this one.
Not selection sort, sorry. What am I saying? This linear search, sorry. Selection sort is already covered. Sorry. There is another searching algorithm that I have discussed another searching algorithm, which is linear search. So can you write this linear search algorithm? It is similar to this process. You may use the function or you may omit the function. You can directly write. So I know that you guys can write these codes in any languages, in other languages that you are comfortable with. But try to write the simple linear search in C. I hope the linear search algorithm is clear to everyone, that you just have to compare every element with the key from the beginning to the end. So can you write that one using just simple for loops would be fine, right? To do that. So try that one. So are you trying even to write? You should try on yourself, no? This one. That's a very simple. Just remove the function. Remove the function. Just write the main. It should be same. Just use the for loop inside. Yes, I think it's fine. So is my screen visible? Can you guys see my screen? Yeah, wait. So let's see. I think the code is fine. Yeah. So yes, your solution is correct, and of course it's correct actually. Okay, so it's very easy. You may not
like you have used the function, you could directly write that code. You don't need to use the function even. So it's fine. Now, now to do what? I've done these two codes. Searching is complete. So let's solve one problem. Yes, yes, I've seen that. But you could have like omit the function. Yes, there is no need. And yeah, that you can just write directly inside your uh, main function. You don't need to use another function. Anyway, it's a good code. So good work. Next, the next problem is would be an application of this binary search technique that you have learned. Can you so you know that square root of a number, finding square root of number, have you heard about this problem? Like given an integer n, find the square root of n. So there is an inbuilt function in here. If you use math.h header file, and if you write sqrt n, if n is the integer that you want to find the what I can say, the square root of n. So if there is sqrt n, will give you the square root of n function. So is there any problems? Okay, so binary search. So now we'll do another example of binary search, which is so why it requires input like 24, 25. In which case are you talking about? Which problem? Is it the linear search, or is it linear search, or it is a binary search? Which problem? Okay, so you gave input 24, 25 in this way, unsorted. See, if your array is unsorted, it will not find. Because in binary search, your array has to be sorted. Okay, in the unsorted case, you can like you have to use this linear search technique. In binary search, you cannot use the unsorted array as an input. Okay, so if you use, then you will get the wrong output. Okay, fine. Any other queries regarding this binary search and linear search? Okay, so we are talking about a problem, actually an application of this binary search. I hope you have heard about finding square root of a number. Finding square root of a number. So square root of a number can be determined using this binary search technique. And also, like there is an inbuilt function in there. If you use the math.h header file, then and you use the command sqrt, that function sqrt, it's corresponding to the square root of an integer. and of course sqrt n is the square root of n. So can you write a code? Like, can you design first? Let's think about the design. Can you design an algorithm that finds the square root of n using this binary search? I mean, think about like how to find square root of n. You want to find square root of n. So what to do? Like one trivial way is that you start from 1 and you walk up to n and you check each number and their squares, whether it's equal to n or not. And if it is equal to n, if some number, you find some number from 1 to n, whether they have like the square of that number is equal to n, then you know that this is the square root of that number. But can you find a better way to do that? So also, like, I'm only interested in the integer values. It's not like you have to find the exact square root of that function. You can give the upper, like the ceiling value. Okay. So I'm happy with the nearest integer, which is like, so let's say if your square root is between 10 and 11, I'm happy if you are finding 11. So can you think about some way to do that? Think about that, like how you can apply binary search in this case. So binary search, also one important input about binary search is that this is this is the divide to conquer that I think I have already discussed. It's a divide and conquer, and in the divide and conquer, your target is to divide the problem into two parts, and into not two parts, I mean into many parts. You can divide it into numerous parts. So your target is to divide the problem into some smaller problems and solve that problem, right? So can you think of a way that you have to find square root of a number? How can you divide? Of course, that square root must lie between the number 1 to n, right? So if let's say n is a number, let's say you want to find the square root of let's say 100. So the square root of 100 should lie between 1 to 100, right? So you have to find all the numbers. So just you have to check in this interval, right? All the numbers between 1 to 100. Now, can you subdivide this interval in some way that you discard one half and you just interest in one half? How can you do that? So can anyone find an algorithm? Anyone? Like how we can? Okay. So actually the idea is simple. So the idea is simple. You just have to see. You will divide the whole space from, let's say, numbers from 1 to 100 based on like uh, you check the middle element again. That's how you are breaking. You check the middle element and you check this is whether in this case it is you find the square root of that number. So if that square root of if the square root of the middle is greater than the number n, that means what? That means why do you search? Why do you need to search? So if it is greater than, that means the number is higher. So your square root must be within this 1 to up to that middle value. Okay, so you search in that space. You don't need to search the other half. You can discard the other half. And also, like if your square of the middle is smaller uh, than the integer n, then you can find then you know that either it would be like equal to n, or you have to search the space between middle and n. Okay, the square will lie inside. Okay. So you can discard the other half. So that's how you can proceed. So do you want me to write this one in the copy so that you guys can understand? I think okay, I should write. Shift to writing. So now the problem that I'm talking about, finding square root the number. A number means basically we are integer, focusing on integer. So how to do that? Okay. So you know that what I mean is that if x is square root of n, then you have this formula that x square equal to n. Right? You have this thing that x square equal to n. So all you have to do is now also you can check that this x should be less than n. Okay, x must be less than n, otherwise this will not hold. And if you take two numbers x1 x2, okay, and if you square them like x1 square and x2 square, okay, just keep. So you consider let's say you consider two numbers x1 which is less than x2. Okay, so it's easy to see that x1 square should be less than x2 square, right? These are the facts, right? So this implies that if your square, like if square of one number in here in this case it's x2, which is greater than some other number which is in this case x1, then the numbers are also in order, like x1 should be less than x2, right? Okay, so we use this fact to design this algorithm. So from since we want to find square root of n, it's easy to see that x must be in this set 1 to up to n, some integer, and also we're just happy we are not finding the exact root, finding the exact square root. We're just finding the it's okay. We are looking for the like nearest integer. Of the square root. Okay. So now we use divide and conquer, which is actually this is nothing but a binary search. So how this binary search occurs is that you find find the middle element of this 1 to n. So we can think of this as a sorted array. We can find the middle element and we check if mid square is less equals to n or not. So if your middle square is less equals to n, so that means that if you take the middle and square it, still it's not reaching n. That means the number at which you can get the uh, square and the number x for which you have x square equal to n, this should be either greater or equal to mid. Okay, so you have to search in the space between middle and n. So you searching now you searching this mid up to this portion. Okay, you can discard the rest of the 1 to mid minus 1 portion. Otherwise if the mid square is greater than n, then you know that it's already exited n. So you have to consider the smaller portion onto it. Okay. So this is the algorithm. So now see, if you like also in here in the first case, you can store the value of the mid, and you can keep on doing this, and you will find the it's exactly same as binary search. You can keep recursively, you will find the square root, or at least the value which is closer to the square root. Okay. So is it fine for everyone? Or any question? No, not for negative. Not for negative. No, square root of negative is not possible to compute uh, in this case in computers actually. So we are dealing with positive integers only, and positive integers. I'm not talking about floats. Even for positive integers, actually the square roots are sometimes like having decimal numbers. I mean having this float type numbers in there. I mean rational numbers, or uh, like in some cases maybe irrational. So still I'm not considering those numbers. I'm just focused on the integers. For example, if you are finding say root of 3, square root of 3, you will be ended up with like 1 or 2 maybe 2 with 2. Okay, so this is how we are dealing with this problem. We are not thinking about like exact solution. We are just trying to find the nearest possible. Okay, and I hope it is clear that how the technique works. It's the same algorithm. So can you just modify the binary search code that I have written uh, in the class to this one to find the square root of n. You just have to change the input. Okay, and you can write the code. Yeah, okay. So I'm giving you some half an hour. You can try and just let me know. Whenever you are done, let me know. Okay. Yes, I'm checking the code. Oh, no. It will not work like that. Okay. Uh, this one actually the problem is that if you change the square root, see, keep the number. Okay, keep the number. Right. Okay, keep the number and you search in there. Okay. Yes, it's a correct. Correct. Okay. Yes, I think your code is correct. Just let me verify it. Just let me check if there is any error. That as per what I see that your code is correct. Okay, you are running with the loop. Yeah, it's correct. Yes, that's what I'm going to show. That how you find it like uh, directly. You don't need to use this one, and this header file will be helpful. Math.h. Yes, it's the header file should be math.h. Okay. So this code that is shared with you guys, I think who is you? Roshan. Roshan, the code given by Roshan is correct, so you can follow that code. Whoever wants to write, or there is a actually simpler way to write this one, uh, but it's okay. Like you just change the code from binary search to this one directly. In math.h, it's like after. Okay, let me share my screen, then you will understand. Okay, I think my screen is visible. So there is an internet issue. Not able to connect it to my laptop. Just wait. I think you can see my screen now. This one is another code. It's the same thing. Square root of n, finding square root of n. I've just used like it's the same technique. Instead of using the recursive call, I just did it in one single call by the function. Just run the loop inside to compute the values directly. So you can follow this one. You can follow this one. I am putting it in the chat. Now for the inbuilt function. So this is another feature. There are some inbuilt function. So this inbuilt functions are accessible through this header file called math.h. Okay, so let me write it. Math.h. Now this allows us to consider the to use this function square root. So you can directly, you don't need to use this function. Just we erase this the whole function. You can directly go here, scan the number, and write integer. The only problem is that sometimes the square root may not be in. See, this function is not will not actually uh, give you the integer. Sometimes it's depending on the value, the square root you want to find. So if you like, you cannot get the exact value. It will give you like if it is a float number, it will give you the I think it will give you the closest possible integer. I mean the largest integer close to the value. So maybe like if your answer is 1.7, it may give you 2. Either it will give you 2 or 1. Okay, if you are setting your answer to integer, you can set it to float. You can set it to double. There is another thing called double. So you can set it in any type, any type of variable. Of course, number variables that you want. Okay, it will give you the answer. So there is no bound on the number n. You can it doesn't need to be integer always. Okay, you can use any number in the square root function. So you can directly use this command square root n. Let's say 25. So it will give you the answer directly. Math.h allows you use a lot of functions also, a lot of other functions that you can directly use. So we are going to use these functions when we like do some complicated coding maybe later on. C. Might not need this function right now, or even math.h. Okay. So, any other questions from anyone? Okay. So, based on these techniques, this divide and conquer, not only binary search, this divide and conquer technique is very important actually. You can solve a lot of problems. Have you problems like using this technique? Have you ever heard of a problem like matrix multiplication? I think you have heard of matrix multiplication problem, right? So, have you heard of this matrix multiplication problem? If you know what is matrix multiplication, you can do this matrix multiplication problem, uh, or rather, forget about matrix, just simple multiplication of large numbers. Okay, that can be done using this divide and conquer technique. So, given two numbers, there may be large. You can like use this multiplication method. There are some actually well known algorithms that solve these multiplication methods in multiplication of large numbers, that uses this divide and conquer technique. Okay. The same goes for matrix also. We can do matrix multiplication using divide and conquer technique. So these problems are very interesting and has applications. So you will find a lot of divide and conquer technique, divide and conquer problems if you look in the internet. I would suggest that if you guys are interested in like coding, not in C, not only in C, I mean in any language you prefer, my suggestion is to like solve these problems as much as you can. Okay, because this type of this type of problems may like appear later when you are going for interviews or internships. Okay, so my suggestion is that try to solve as much as you can. Uh, Focus on these techniques and try to find the solutions first on your own. Then if you are not able to, you can look at the resources, and you can pick any coding language you want, but solving those problems, like designing the algorithm, that actually the uh, that's actually what matters most. So how you are tackling the problem, it's the important thing. So use these kind of ideas, use these techniques, and try to solve the problems as much as you can. Okay, so and also like in C we I think today we done much. Today we only covered this binary search and mainly searching algorithms. So I think in the next few classes you will be introduced to this divide and conquer application of this divide and conquer techniques. So see some other algorithms. Maybe there is a multiplication algorithm that I was talking about, Karatsuba multiplication algorithm. Maybe that will covered in your class, and we'll see that in the next class maybe. Uh, okay. Uh, for that, I think I don't need. Yes, you can practice in any. You can practice in any platform you want. Uh,
it's good to practice this kind of problems, especially like focusing on like not only writing the code, it's about the design of the algorithm. The focus should be how you are designing the algorithm, because a problem can be solved in many ways, and mostly what is expected is to uh, like you can find it, like you can find it in Geeks for Geeks, you can find it in Lead Code. There are a lot of platforms. Okay, Geeks for Geeks is actually a very good platform. Yeah, there are like they are designed for subject specific coding problems, not only coding problems, also theoretical problems. So if you are not able to solve one, you can look up the answer and then you can check. And uh, what I was saying is that hmm, it's not about the code. Okay, it's about how you are doing the solving the problem. Your uh, when you are solving one problem, your running time, I mean, the running time is what matters actually. If you are solving, you can solve any of these problems in that we have seen in binary search problems. You can do it in linear time, but it's expected to do it in order log n time. So it matters that how you are solving a problem. So I would suggest that first you should focus on designing the algorithm, like how when you face a problem, how you solve it. How do you solve it? That should be the first focus. How efficiently you solve it. First, let's say you come up with the solution, then you can check that whether the solution can be improved or not, and then you can go for your coding language and you write the code and all. Uh, that's a another thing, but the focus should be like improve your algorithm. I mean, improve your designing ability. Uh, okay, fine. Right. Okay. So we'll see. We'll meet in the next class. And in the meantime, I think those who have problems in C, you can check these codes that we have done today. They are very easy codes, and maybe in the next class we will focus on this basics of C, where we have already seen a lot of basics. I think I have not done anything using this pointers and all. We'll see the pointers and their application, and maybe some other like data types also, like for I have not used float, I have not used I think I have not used character, I have not used string. So I have I would uh, I have to introduce them somewhere. I think in the next class I will introduce them. Okay. And see, it's very difficult to cover the basics in this class because I have to deal with the algorithms too. So what I am doing is that I'm giving you the idea when we are solving one problem. I'm giving you the idea behind it, like when we will be using these pointers and all and other data types, then I will I will discuss about them. But to like thoroughly cover the basic things would be very difficult for me at this stage. Today I used one problem. I think in if you look at the this square root problem, I use while loop. Okay. Have I discussed while loop? I think I discussed while loop in the last class or maybe last one. Uh, I have discussed all these loops that we need. I think I have discussed for, if, and while. mostly we need these three. And I have discussed about this header files. I think I have discussed about a standard library also. I have discussed functions. So you need these are the main things that you need now. But like completely covering the basic is actually very difficult for me in the time bound. So I may not be able to cover. Yes, you can view online sources. That's very helpful actually. Online resources are always good. You can follow them, and then you can follow this class. That would be helpful for me too, so that I don't have to cover like all the things in here. And I hope that you will get it easily. Okay, fine. Okay, so I'm stopping this class. Thank you. We'll meet in the next class and we will discuss about I think next class will be divide and conquer application, and maybe we need to see some basics, some of the other type of variables, and let's see what's in the class. Maybe this will be in the next class. That's what I am thinking. Okay. Okay, thank you everyone. We'll meet you in the next class. Good evening.